So our next speaker will be Kathi Fisler, and hopefully the system will come up quickly this time. And there it is. So on we go.
Okay. So like many of us, I'm here partly because of 511, but the Dan moment that I wanted to talk about briefly actually was in 611, which is Dan's class where he walks in, tells a story or two or five, and each story has a problem that's really hard to think about, and he just keeps throwing these at you, and you're supposed to keep working on them, and at the end of the semester he decides roughly how many of them you more or less got, and that determined how you did in the class. So I remember there was one problem that I was working on, and I just wasn't quite getting it. And in Dan's style, you would send a mail and say, I'm a little stuck, and he would say, well, come on over to the house and let's look at it. Okay, so you drove over to Dan's house, and he'd send you home with some hints, or he'd send you back some hints by email. I worked on this one problem, I don't know, it must have been a good couple of weeks, and I sent Dan mail, and the message that came back said, call me. Okay, so I called him, and he said, give up. Yeah, okay. He said, look, move on, try some of the other problems. It took me a long time to realize that what he was trying to tell me is that problems teach you things. And you'll hit a point where you've learned everything you're going to learn from a problem, and then you should go learn something from another problem. I did give up at the time. I will admit that I am still trying to nail that problem. I mean, and if I ever get it, I will mail it to you. So, okay, so the talk I'm going to be giving here is on verifying aspects modularly. There is no scheme in this talk. There is no programming languages in this talk. So why on earth are we giving it here? Well, it's because of the co-authors. This is a group of co-authors that owes their collaboration to Dan. So it's a fitting combination. Why is that the case? Well, at lunch, Shriram briefly mentioned how Dan was letting him think about problems from 511 and 611. What he didn't mention is that our early dates usually consisted of him coming over to IU so he could go to Dan's classes. And it was never really clear which one of us he was coming to see. So Dan played a big role in cementing the early part of that relationship. And
I want to tell you what Michael's role is. So I get an email a year ago from a student who was using a Brown address, but he's using the university-wide mail system, not one of the computer science account addresses, like an IU Vax mail account, and says, hi, can I come and see you? Dan Friedman asked me to get in touch with you. Okay. He's not a CS student, so I figured maybe it's a personal friend of some sort. Certainly, come on in. Comes in and says, so what's your connection with Dan? Well, I'm a freshman here at Brown, but my connection is I took this course from Dan called 311 back last year when I was a high school student. I very quietly got up, ran to my door, shut it, locked it, and said, I'm not letting you leave till we figure out something that we can collaborate on. Yeah, that's what we got.
He's great. Thanks a lot. Okay, so let's get into the problem here. All right, so very briefly, normal outline talk, going through a little bit of aspects and some other material. You've heard a couple of talks on aspects the last couple of days. So what do we see aspect-oriented programming as being for? Well, there's two primary points of view. One is invasive software injection. How do you modify program behavior by injecting code into it? Another point of view is that it's really a new form of modularity. And one of the characteristics of this is that you have composition that can be predicated on execution. And that's very different from a lot of the module systems out there. Now, there actually is a third point of view that sometimes comes up, especially if you're in my world. So I was a minor in Dan, not a major in Dan. I'm actually a verification person. And if you're in any kind of the formal reasoning world, yeah, right. This is not a good idea. If you want to know
what this is a new form of modularity, you're sort of saying yes in the sense of no.
Good. So, what does this mean? Well, for somebody like me, this is great. We got to think about verification. Now, what do we mean by the verification problem here? Well, AOP is going to add code to existing programs. And you may have properties of that original program that you'd like to preserve. How do you know whether the aspect that you've added is going to break that property that you had before? So in this talk, what we're concerned with is determining whether an aspect is going to preserve properties that you've already proven and want to preserve about a program, and we're specifically going to be using model checking. Okay, so now back to our outline. Talked kind of very briefly about aspects. Now I want to try to get in a little bit to the verification algorithm.
Is this the same kind of verification that Sriram was talking about earlier?
Not exactly.
Don't you think you should explain that to us?
Okay. Yeah. Let me think about that.
Okay. While Kathy's thinking about this, let me try to give you some perspective on what's going on. What is a talk? A talk is a program, right? A talk has some sequential flow of control. It's got sections, right, which are like subprograms, and it's got individual slides, which are essentially your little pieces of control. And what we have here is called an outline, but another way of looking at it is that's a control flow graph, right, for our talk. And what Robbie wants Kathy to do is to add a new chunk of control into the program by replacing the existing control flow graph. Okay? This is an instance of aspects at work. So this is our base program. This is the advice that we want to give, the advice that Robbie just gave. And the place where we want to insert this new advice is known as the join point. So I need to teach you a little bit of aspect terminology for the rest of the talk. Okay? What's a join point? A join point is a location or an operation where some new code can be inserted. Okay? Now in an aspect PowerPoint, which will no doubt exist in a year or two and it'll probably have an XML notation, the points where you insert new behavior might be slide entry, section entry, and so on. In a traditional language like Java, it might be at a point of method invocation, point of field access, a point where you spawn a thread, and so on. These are the primitive points where you decide the behavior of a program can be altered. The advice, this will be familiar for all of the Lispers in the audience, is how do you modify the behavior? There's our before, after, around, the usual stuff. Okay? Finally, one new term I need to teach you is something called a PCD. So we said that there are join points where you can change the behavior of the program. But do you want to change the behavior at every join point? Chances are you might want to change the behavior only at some subset of the join points. The PCD is how you designate which of the join points you want to change the behavior at. What we will use in this talk is a notation that's due to Ugo de Moore and Damien Sereny, which is if we want to say we want to change the behavior at the section verifalg, right, before the verification algorithm, we might write a regular expression that looks like this. P is a join point, a PCD. It says this is the shape of the stack at which we want to insert new behavior. So there's a bunch of frames which we don't care about, but if the top frame is the beginning of the section verifalg, that's when you want to change the behavior. Does that make sense? That's a regular expression on the shape of the stack.
So section is a predicate on an implicit argument. That section verifalg is a predicate on an
Excellent. It's the predicate on the top frame, stack frame. Good. And so every advice has to have an associated PCD with it. So to recap the terminology, okay, the PCD is, that's the point where I want to insert the behavior. The advice type is, before we get into the verification algorithm, as Robbie said, I would like you to tell me a little bit about the model checking algorithm. And finally, the advice itself is the model checking section of the talk. Okay?
The talk is a stack, and we're going to get back to
Yeah, but if you let random people insert things into your
Yeah,
talk,
I'd
then
like
it's
to
obnoxious.
That's why you need a verification technique, so shut up and listen now.
Are you the stored continuation?
I am indeed the resumed continuation. So, as a resumed continuation, let's go into a brief overview of model checking. This is a slightly different version than the kind of model checking Sherm was using earlier.
Did you answer Robbie's question?
I'm about to. Okay. So, what do we mean by properties? We're usually talking about temporal properties concerning behavior. So what might you want to know about a talk? Well, how about that it always eventually reaches the conclusion? Okay, that's one good property. Another might be that I'm not going to talk about the implementation, before I get into the verification algorithm section, right? So somebody could try to advise me to put material out of order, and we'd like to be able to check against that. How do you write this? Well, formally, we have things called temporal logics. If you are familiar with temporal logics, we're using one called CTL. It's a branching time logic. That's irrelevant if you don't have experience with this. But what this says is, on all paths in the future, I'll get to the conclusion. That's how you read one of these. And the second property would say, on all paths, I don't see an implementation until I've seen the verification algorithm, and there's an expectation here that you will eventually do a section on the verification algorithm. Showing this just as an example, you don't really have to understand the logic syntax for the talk. Okay, so how does model checking work? Let's consider this property that says I don't do an implementation section until I've done the verification algorithm section. What the model checking algorithm does is enumerate all of the subformulas of the formula we're working with. Okay? So we have the two propositions, implementation and verifalg, not implementation, and then the whole formula. Those are my subformulas. What I'm going to do is go through these subformulas, bottom up, one at a time, and label the states of my state machine that satisfy each of those properties. So if we just look at the implementation state, for example, it satisfies the implementation proposition, but it doesn't satisfy any of the others. The verifalg state, for example, doesn't satisfy the implementation, but it does satisfy verifalg, not implementation, and that there's no implementation until you get to verifalg. That's kind of trivially true. So this is what the algorithm's going to do. You'll end up with these labels on all of these states. What do you actually need to know about this algorithm? It's the following invariant. When the checker is done, every state has been labeled with exactly those subformulas of the property that are true at that state. Okay, this is the piece of the model checking algorithm we're going to depend on crucially, and we're relying on the algorithm to do this for us. Okay, so now let's get into how we actually verify aspects. Here's my original program, and I've got the labels on there that I generated for this property. And when I insert this new model checking module, I need to make sure that I don't violate that property. So there's the new set of slides. Now, how am I going to determine whether I've violated the property? Well, what we mean by checking the property is that the desired property has to be true at the start state of the system. That's what we mean when we say it's been verified. So if you notice, before we added this, in the set of labels for the motivation, which is the start of the talk, we do have the property that we don't do the implementation until we've done the verification algorithm. Now that might have gotten violated when I insert this. So what am I going to do? Well, how much of this original state machine do I really need to think about the impact of this new piece? Well, it turns out all I need to keep are the states that it connected to. Why is that? Well, let me get rid of them for the moment. The way model checking works, since these properties are talking about future conditions, whatever's true in here is going to derive from whatever was true at this point. These labels are summarizing whatever happened in the rest of the system. So by knowing what was true here, I could determine what I need to know about the states here. And what is it that I need to know? Well, okay, I'm going to assume these. I need to guarantee that whatever I proved about that aspect state, which is where I came into this new part of the talk, let me prove that I didn't lose any of those labels. Okay? Why was that important? Because everything that came before that aspect state, those truth values were determined by the labels at the aspect state. So if I can prove that I didn't lose any of those labels, there's no way I affected anything before it. So simply by remembering what labels were true at this exit point and what ones I need to preserve, I can run a version of the checking algorithm that will confirm all those labels given just that information.
Isn't that stronger than you need that? Is
It is potentially stronger than you need if the property didn't actually depend on those labels. Yes. So it is sufficient, but it's not necessary. Yes. Okay. So we need to generate an interface in some sense for that base program. When we have the labeled base program, we're going to automatically record the labels at those connection states, and from that we can drive this analysis process. And these labels are what give us a behavioral interface. But now that leaves us a question. Where are those connection states? Right? That's the key, knowing which of these labels you actually need to save. You don't want to save the labels on everything. That's going to get potentially quite expensive. How do we get the connection states? Okay, where did we start? If you think about what aspects do, we started with these PCDs. They're telling you where I might apply advice. Right? And they're telling you what kind of advice you're going to apply. The advice itself is irrelevant. I just need to know where is it going to go. Okay, this case is easy. If I find the verification algorithm section, I'm going to hook up that new section at the predecessor state. All right? So from this specification, I can locate the states at which I actually need to save those labels. So let's look at a more interesting example. Let's say you wanted to insert some material after the slide on the property examples, but while you're still in the background section. Maybe I need to do more detail on the logic for a different audience. As a PCD expression, this looks like the following. So this is saying, what does the stack look like? Well, we've got some stuff on the stack, a background section, some more stuff, and there's a property example section at the top of the stack. Okay, that's the predicate. So the connection states in this case are at the property example slides, but in the dynamic extent to the background section. If you're in the aspect J world, this is called a C-flow. And this is, again, what makes aspects particularly interesting from a verification standpoint. An observation here is that these PCD expressions, well, they're regular expressions. So you should be able to compile them into finite state automata. And if you do that, you now have your program and these PCDs as automata. You could cross-product them. And that should help you locate these states automatically. So the automata are fairly straightforward, right? If my PCD says some stuff on the stack followed by verification algorithm, well, there's a bunch of stuff, and once I'm in P2, I'm actually at the point that I want to trigger. Similarly, the second PCD, it's a 3-state automaton that just detects the 2 stack frames that I'm looking for. So here's my program again, my base program. And I've got this PCD. If I cross-product this PCD with this base program, I effectively get these state labels. Okay, I'm just going to put these on as saying which of the states from this PCD I actually reach simultaneously with this cross-product. So what this is telling you is if I look for state P2, which is right here, that's where I'm going to be inserting material. If I have before advice, the new code is going to replace this edge. After advice replaces that red edge. Around advice could bypass this altogether and go in that location instead. Okay, now let's take a look at Q, which is our second PCD. And again, here are my labels. Now notice about Q. Q is a 3-state automaton. Nowhere here do I have a Q3, which means that this program by itself is not going to trigger Q. Okay, we need to keep that in mind. Now let me add my advice. There it is. And I want to verify this property. Now, this PCD here should pick up this property examples state. Because once I have the combined program, the base plus the advice, I do actually trigger Q at that starred state. The advice alone doesn't do it. The base doesn't do it. And if I'm really going to pick up all the connection states, I have to detect that. And again, I want to do it without having a reason about the whole thing together. We're trying to do this in pieces. But at that aspect state, I had that information circled at the top. What state was each of those PCD automata in when I started this advice section? From that, I can then go ahead and extend my labeling to the advice without having to go back and recross product the whole system.
Kathy, but you can't do that until I tell you where I'm hooking it in, right?
Right, I need to know where you're going to be hooking it in. So, what does this tell us about the interfaces? We said before we needed those labels. We also need to close the interface over where the state of those PCD automata. So, our interfaces now consist of these two pieces of information. Where were the PCD automata? What were the labels? All of this can be generated automatically from the PCDs. We're really interested in doing this as automated as possible. Now, this is the very high-level version of this. What are some of the subtleties that come up? Well, the first one is that the PCD automata leads to a multiplicative factor in the machine size because you're doing cross products. And as Shriram mentioned this morning, the biggest pain in the neck, if you're a verification person, is state machine size. That's the limiting factor for us. It's space, far more than time. So this approach, as I've outlined it here, is probably going to blow up and be a serious problem. What we have is a technique that can actually use the model checker to detect these states without actually doing the cross product. If anybody's interested in this, feel free to ask me during the break. I can show you. It's cute, but it's...
The one-sentence version of it is...
The one-sentence version of it is we take those expressions. Those regular expressions look a lot like temporal logic formulas. Instead, we treat them as temporal logic formulas. The model checker is going to do this labeling for us to find where things are true. And we can use that labeling combined with the temporal logic version to get us where we want to go. Again, with a couple of subtleties to make it all work in practice. Another good subtlety is that a round advice can eliminate program paths. That can really screw things up. We know how to get around it. We've got modifications to this algorithm that accurately figure out what you could not need and patch around this problem. You can also eliminate states through the around advice. Actually, the program paths come out even with before advice because you've taken out that one-step transition that you had between two states before and replaced it with something else. Both of these are things we know how to handle. I'm just not talking about them here. And you also have the ability to use proceed in the around section, which can jump you back into the code that you thought you might have otherwise bypassed. Again, these are all things we know how to handle. We're working on an implementation of this for Java and AspectJ in particular. We're building it on top of a well-known model checking framework for Java called Bulgur Bandera. We had to build a model checker for this framework. It didn't have all the pieces we needed. So we're working on the translators that we need to feed AspectJ into this tool as opposed to just Java, which is what it was built for. And there's some other technical things we're working on. But we are building a tool that would actually do this for AspectJ programs. Okay, let me just wrap this up with a little perspective. We're claiming that you can indeed verify aspect advice modularly. The caveat is that we have to know the PCDs statically. We don't have to know what advice is going to go there. We do need to know where you're potentially going to hook them up. And this works even if your PCDs are stack predicates, the CFlow style things, instead of very simple things like at this program call, the static kinds of PCDs. In order to do this, what information did we need to remember? Well, we needed constraints to help us preserve properties, and sufficient information to extend the point cuts. These were the labels from the algorithm. These were the automata labels from the PCDs, which I showed you earlier. Now, you might say this sounds a little strange. We're generating interfaces for modules automatically and preserving properties. Why does this work? It works because we are generating interfaces specific to properties. We are not generating most general interfaces for modular reasoning. Okay? We are saying, if this is the property you want to preserve, what interface do I need? That's what makes this tractable, both theoretically and in practice. And that's what we had to say.
Now that her talk is over, Andy would like to make some advice on ways she could modify the talk at this point. Or questions, sorry. Yes.
Okay, so when you have the the, like you can compute that, and then like you're adding more, and then you're computing the sub portion. Like if you have a path from the end, I don't see why the cross product is the same coming out.
Right. So why is it okay when we're at this point? How did we not affect the labels on this state? Right? That's a good question. The thing you have to remember is the stack is context free. Right? We are approximating it with a regular expression. Because of that approximation, what this is effectively the pop. Okay, that's largely what's going on there.
It doesn't even matter that it's context free. The whole point is when you're done, the stack is in the same state it was in when you went into the advice.
So I mean, I think
it's a method invocation. When the method invocation may add all sorts of junk on top of the stack. When the method invocation is done, the stack is back to the same state it was in when it went in.
So you have a correct observation that if I took this whole thing and did that cross product, the labels might look a little different. But this is the correct labeling because of this stack copying behavior. And the optimization that I talked about, that I didn't go into detail, but that I mentioned, actually looks at this graph backwards, and that gets us around the problems of stack copying. So everything actually comes out dead on accurate because we look at the graph backwards.
This is really interesting because it seems to provide a mechanism that will give you the flexibility of aspects and yet sort of block out their unconstrained evil. So what I'm wondering is, how does it work out in practice? We tried it out on
well, this is why we're building the tool suite. So what the story of the tool suite is, we thought this was going to be easy. This tool set we were building it on, we believed had a number of features that were going to make this not too hard to do. And it turned out a lot of the things that we had expected to be in that tool suite weren't available. I mean, you need
For instance, it was a model checking framework without a model checker. Okay. So it was just a framework.
So it's taken us longer to get this off the ground because we had to build a lot of model checking technology that the model checking guys didn't build into it. So as soon as we get this tool finished, we are going to be running it on that stuff.
Have you thought of treating this thing as a type system in a programming language?
Sherm, you want to take this? He's the
What
language.
did Jerry say this morning about type systems? I think what it could be interesting, it's just I've never seen effective ways of encoding good temporal information in type systems. And the properties we're working with are temporal, right? So I don't know how one could easily do this. I don't know what such a type system would look like. Type systems are really not very good for things for dealing with temporal information.
Yeah, but they have this very nice property that people who use don't understand.
That's how complicated
It's aspect-oriented programming.
Depends on which type. I mean, Russell?
No, aspect-oriented programmers. Programmers in general, they understand.
Well, I mean, there is a problem with what we're showing here, which is that somebody has to write down a property, okay? So we're not getting around that problem. If that's what you're getting at, yes, we do ask for somebody to write a property. On the other hand, if somebody writes a property, the rest of this is essentially push-button technology, right? Because this is why we kept emphasizing that the interfaces are generated automatically. As opposed to a traditional type system where you have to write the interface declarations, this idea of property-driven interface generation derives it for you automatically. So I don't know how much easier you could get other than the fact that somebody has to write a property down.
Kathy? Yes, Matthias?
No, I'm not going to stick them in there, whatever they are.
What was the problem? 511, 611.
Oh.
She wants to solve herself.
Yeah, don't tell me how to do it. Okay, this was the same fringe. You're supposed to do same fringe without creating any additional memory. So no cons operators anywhere in your solution to same fringe. And I got it down to one darn cons operator that I still can't get rid of. That's the problem.
Dan doesn't believe the call CC allocates memory.
Wait, does call CC allocate?
No.
Call CC and the lambda inside of it for free.
Right.
That was the constraint.
Right. So you were allowed that, but that was it. So yeah, that.
And I do know that it uses it.
Yeah.
Now. Any other questions? Well, I guess that's it for this session. We will see you at 4 o'clock. everybody.